Elements have different properties because they are made up of different atoms. The atoms differ in the number of subatomic particles that they have. There are three basic subatomic particles. The first is the proton. A proton has a positive charge. The symbol for a proton is often written as a P for proton with the charge shown up in the top corner. The next one is the neutron. Neutrons don't have a charge. They are neutral. So we write the symbol for a neutron as an N with a little zero, showing that it has no charge. The third is the electron. We write the E for the electron and show that it has a negative charge. Most of the mass of an atom is found in the nucleus. This is where we find protons and neutrons. The extremely fast-moving electrons are found outside the nucleus. We don't include them in the mass of an atom because they are so very tiny. They're nearly 2,000 times smaller than a proton and a neutron, which have similar mass to each other. Although the electrons are so very tiny, they actually occupy most of the volume of an atom. Now this diagram is exceedingly not to scale. Just for a size comparison, if an atom of helium, which is the smallest atom, if it were the size of the moon, it would be roughly 3,500 kilometers across. The nucleus of this very enlarged atom would be about 71 meters across. So whilst the nucleus has most of the mass, it's actually only a tiny, tiny, tiny part of the whole volume of an atom. In this scale, an electron would be about 4 centimeters in size. So the electrons really are very, very tiny. But they take up most of the volume of the atom because they're moving around the nucleus so very, very fast. The atomic number of any atom, symbol Z, capital Z, is simply the number of protons in the nucleus of the atom. That's a simple definition of atomic number, is the number of protons. Each element has a specific atomic number. For example, the atomic number of hydrogen is 1. Hydrogen has 1 proton in the nucleus. The atomic number for lithium is 3. Lithium has 3 protons in the nucleus. It's the atomic number, the number of protons, which actually defines what an element is. As an example, anything that has 16 protons is sulfur, because the atomic number of sulfur is 16. Anything with 23 protons is vanadium, etc. The mass number of an atom, you can think of it as the number of things in the nucleus. Now, in the nucleus, we can have 2 things, protons or neutrons. So the mass number, symbol A, is the number of protons plus the number of neutrons. Remember, the electrons aren't found in the nucleus. The mass number is also referred to as the atomic mass or the atomic weight. Either of these are fine as alternative terminology. However, do not simply talk about the weight of an atom. Weight is a force, and as so is measured in newtons. We can get away with atomic weight for historical reasons. In an unreacted atom, the number of protons is the same as the number of electrons. So if we look at boron, the number of protons is 5, because boron has atomic number of 5, boron will also happen to have 5 electrons. In a similar fashion, calcium has an atomic number of 20, so calcium has 20 protons. Calcium will also have 20 electrons in an unreacted atom of calcium. But remember, the atomic number by definition is the number of protons. So if you're asked to define the atomic number, don't say it's the number of electrons. It is the number of protons, which will happen to be the same as the number of electrons, but it's not defined with the electrons. Because unreacted atoms have the same numbers of protons as electrons, this makes atoms neutral overall, because all of the positive charges from the protons cancel out the negative charges from the electrons. It's this attraction between the positive and the negative which holds the electrons in place, orbiting around the nucleus. Electrons aren't just orbiting around the nucleus in random patterns. They spin around the nucleus in shells. Each shell has a certain maximum number of electrons that it could possibly take. This number is given by 2n squared, where n is the shell number of the electron. Applying this simple formula, the first shell, where n equals 1, if we square that and then multiply it by 2, we see the first shell can take a maximum of 2 electrons. The second shell can take a maximum of 8 electrons, because we have 2 times, it's the second shell, which is squared, so 2 times 4 gives us 8 electrons in the second shell. The third shell can take 18 electrons, because it's 2 times 3 squared, so 2 times 9. So the third shell has a maximum number of 18 electrons. The fourth shell can take 32 electrons, and the fifth shell can take 50 electrons, etc. Electrons fill in the shells in order to form what is called an electron configuration or an electron arrangement. It's written as the number of electrons in the first shell, then a comma, then the number in the second shell, comma, third shell, etc. So if we look at a few examples, we mentioned boron earlier. Boron has an atomic number, Z, of 5. Remember, this means it has 5 protons in the nucleus. But an unreacted atom of boron will also have 5 electrons. So we put them into the shells. Starting with the first shell, that can only take 2. So that first shell will have those 2 electrons. We put a comma, and then we move on to the next shell. Now the second shell can take 8 electrons, but we only have 3 left. So we put those 3 there. This is the electron arrangement, or the electron configuration, for the atom boron. Sulfur has an atomic number of 16. So it has 16 protons. It will also have 16 electrons. So 2 in the first shell, that's now full, so we move to the second shell. 8 into there, that's now full, so we move to the next shell, the third shell. We have 6 electrons left, so we put them in there. 2, 8, 6 is the electron configuration, or the electron arrangement of sulfur. Looking at 2 more examples to finish off. Calcium has an atomic number of 20. Its electron arrangement will be 2, 8. Now we have another 10 electrons to put, and the third shell can take up to 18. But here's the catch. 8 of those electrons go into the third shell, and the next 2, the 19th and 20th electrons, actually go into the fourth shell. If we take another example, vanadium has an atomic number of 23. So for the electron configuration, we have 2, 8. Now you would put 8 electrons into the third shell. You would then put 2 electrons into the fourth shell, but we've still got another 3. But remember that third shell wasn't full at 8. So those last 3 electrons will actually come back to the third shell and start filling that up towards 18. So 2, 8, 11, 2 is the electron configuration of vanadium. So just keep in mind those 19th and 20th electrons, you start the fourth shell before coming back to finish off the third shell.